In this video, we're going to discuss London dispersion forces. These are the attractive forces between the instantaneous dipoles on all molecules. So all molecules have this force. Non-polar molecules like CO2 have no permanent dipole. The carbon-oxygen bond is polar, but when we draw the two bond polarity vectors, they sum to zero. The net is zero. But we know that CO2 molecule A and CO2 molecule B must interact and stick together under some conditions. There must be some intermolecular force because we can make solid CO2. In order for CO2 to become solid, the two molecules would have to stick together to form the solid crystal. So what is the nature of this intermolecular force? Well, to explain this intermolecular force, let's start with an analogy. We're going to start with a racetrack, and on this racetrack there are 18 runners, and we're looking at the race well into it, so they've been running for quite a while, and they're lapping each other, and some people are getting past and some are passing the others. Let's take a photo, a snapshot photo, an instant in time, and look at the distribution of the runners. So here we're going to stop and take a photo. If you look at this photo, you'll see that there are 6 runners on the left side of the track, and there are 12 runners on the right side of the track at this instant in the race. If these weren't runners, if instead these were electrons, I would be able to assign an instantaneous dipole. Here's the vector for that, where the arrow points towards the negative side with the 12 runners on it. Now, if we let the race continue again, and then took another snapshot here, this is another instant in time. Look, the distribution is totally different. Now we have 10 runners on the left side and 8 runners on the right side. So the instantaneous dipole has switched, and it's a little bit smaller in magnitude. If we did a time lapse of this race, we wouldn't see any net dipole because all of the runners would complete the same length, and here I've kind of drawn it where there are a bunch of circles. So the time lapse version is what we usually think about for electrons, where they're kind of time averaged whizzing around in this diffuse electron cloud. If at any one instant there happens to be electrons congregated on one side of the molecule, and therefore a deficiency of electrons in the other, that results in an instantaneous dipole. It's not a net dipole, it's just there for a femtosecond, a very brief moment of time, and then it goes away. On average, there's no net dipole.